So Jordan's lemma says that if you have a path which is just this semicircle here of radius r, then the integral of phi z e to the I a z tends to 0 as r goes to infinity, as long as certain conditions are met. First, we need that a is greater than 0. If a is less than 0, it's actually possible to get the same lemma, but we consider a contour going below the real axis, so that's not a problem. More importantly, we need that phi of z, the modulus of phi of z, goes to 0 as z goes to infinity, and as long as the argument of z is in this region. So basically what we want is that z, phi of z goes to 0 along this contour as the contour gets larger and larger, gets infinite radius. So to prove it, well, we first say, well, we need to actually evaluate this, and we'll consider this integral here. So along the contour, of course, z is equal to r times e to the I theta. So the integral we're interested in is the integral from 0 to pi, theta equals 0 to pi, of phi of r e to the I theta times e to the a. Now, z is itself r times e to the I theta. So, writing it out using Euler, I've got cos theta plus I sine theta in here, and dz, as usual, is just I times r times e to the I theta times d theta. Okay, so what I'm really interested in is showing that the magnitude of this is going to tend to 0. I'll just make one simplification first of all, and that is just to change this a bit. So the bit I'm really interested in, the e to the I bit is just modulus 1, so I'm not really worried about that. The bit I'm worried about is the bit which is not imaginary. So I've got I times I, so that's minus r sine theta there. Sorry, r sine theta, and all of this. Okay, so now what I want to do is say, well, I'm just interested in the modulus of this. So the modulus of this is equal to the modulus of this. And so I'm going to say that this is less than or equal to a quantity which I will then show to tend to 0. Okay, so what I'm going to do is say, well, this thing I can't really say very much about, but if I say, well, suppose I know what the maximum value of this is, then if I were to change this thing here into the maximum value, then the integral I would get would definitely be less than this integral here. So I would just imagine changing this into the maximum value. That would give me an integral which is more than the integral I have here. Okay, so I just take out that as a constant factor. It's the maximum value of phi of e to the I phi, and I'll make it the modulus as well. And this is for all angles theta. The maximum, if I check all angles theta between 0 and pi. So I can take out that constant factor. I can take out this r, which has nothing to do with theta. Now this is modulus 1, and this is modulus 1, this is modulus 1. What effectively I'm going to do now is use the triangle inequality, which basically says that, remember that an integral itself is just a sum. So effectively I'm summing these things, these various things, over all values of theta. Now what would happen is that I would add them together and probably get something reasonably small. But what I can do is use the triangle inequality and say, well, whatever I sum them to, this will definitely be less than the sum of them all pointing in the same direction. Okay, so I can safely say, well, all these are modulus 1. I can then ignore them, and I just get left with the integral from 0 to pi of this thing, which is the thing I should be worried about. Now the problem is that this integral here is too difficult to do, but I can again use the same trick and say that it is itself less than another integral that I can do. So sine theta between the limits 0 and, well, okay, the other simplification I should make, of course, is that sine theta is symmetrical about pi by 2. So actually I just need to work out the integral from 0 to pi by 2 and then double it. Okay, so that makes life easier. But still, I can't do this integral. But sine theta between 0 and 90 degrees looks like a curve like that. And so it's definitely more than the straight line which connects these 2 points. So if I got pi by 2 here and I'm plotting plotting theta here, then this line here is y. This is y equals sine theta. This line here, the straight line, is this is 1 here. So it's going to be 2 theta over pi. So sine theta is therefore always greater than or equal to 2 theta over pi in that interval, which means that e to the minus sine theta, if sine theta is larger, then e to the minus 2 theta over pi will be larger, will be smaller. So I've got that right. Sorry, if sine theta is larger, so that's going to be e to the minus is going to be smaller than e to the minus ar. Sine theta is 2 theta over pi. Okay, so this is an integral which we can do easily. So what do we get? This is equal to pi over ar2. Sorry, it looks a bit strange. 2ar evaluated times e to the minus ar2 evaluated between pi by 2 and 0. And this thing here is equal to pi over 2ar. Sorry, I forgot the minus sign. I'll use the minus sign here to reverse the limits. So 1 minus e. So if I substitute pi by 2 into here, I just get e to the minus AR. Okay, so we know that this integral here, which is twice its integral here, is definitely less than this quantity here. Okay, so I can now, so if I double things, so I just put a factor of 2 in front of everything, just to, and then I get rid of that 2 there. Okay, so this quantity here is the same as this quantity here. So I can, if you like, substitute this relation into here, and I now know that the thing I want is definitely less than this thing here replacing this thing here. So if I do that, I get this expression here. The r, one from here, one from here, cancel. And then all I need now is to say, well, what happens as r goes to infinity if this is the thing? So as r goes to infinity, we've already said that this thing here goes to 0. So this goes to 0. As r goes to infinity, this goes to 0. So we just end up with 0 times pi over a. So we know that therefore in the limit, as r goes to infinity, this quantity gives something which is definitely going to be less than or equal to something which is 0. And therefore we have proved the lemma.